Welcome to my YouTube channel. I'm Yifan. Today I'm going to discuss principle, design and construct about active low pass filter. So what is an active low pass filter? There are four major filters around the electronic circuit. Low pass filter is the one of the major filter while it only allows low frequency signal pass through only. Active low pass filter means the signal after low pass circuit that amplify and increase stability of the signal output using external power source. All N are needed for this procedure, which means it will derive the external power source to increase gain of input signal. There are many applications that use active low pass filter, for example subwoofer system which form low frequency sound, audio amplifier that able to control sound output, and equalizer system. The requirement of the circuit design of this active low pass filter is to design and construct an active filter in simulation and practically. The circuit design should only let signal pass through between 0 until 1 kHz only. The OM is required to apply into the design. Microcontroller and programmable devices are prohibited in this circuit design. Now let's talk about the design planning of this active low pass filter circuit design. After consideration, the first order low pass Butterworth filter are suitable for this design. There are two different types of first order low pass circuits, which are RC and RL. I'm using RC circuit to design due to the capacitor value have a lot of value and easier to find in real world compared to inductor. I have chosen LM358 OM to act as an active filter due to it is convenient and easy to find at local component shop. Besides that, it is suitable for amplifying and able increase stability of the signal. After design planning, now let's talk about the circuit design. This is the schematic diagram of this topic. This circuit design shows in slide can achieve the requirement which allow the frequency start from 0 Hz until 1 kHz signal pass through only. In schematic diagram, there is one OM, 3 resistor, 1 capacitor and 2 power supply. R1 and C1 are RC circuit that mentioned just now. Then we'll have calculation section later. R2 and R3 are used for OM gain control. The OM are powered by two power sources due to some signal usually need to swing bipolar, so the output voltage that go either positive or negative in response to the normal range of input signal. If without the pure power supply, the output signal will clip, which is saturation at the ground potential. Now let's talk about important section, which are calculations and result. To calculate the cutoff frequency of RC circuit, we are going to use the formula which is Fc equals to 1 over 2 pi RC. Fc is equal to 1 kHz, which is the requirements needed. The capacitor value can be any number, so I set it at 10 nanofarad. After sub all the value into the formula and calculate, the answer should be 15.92K, which is the resistor value. In this slide, we will have calculation for magnitude of voltage gain. To calculate the magnitude of voltage gain, DC gain is equal to 1 plus R2 over R3. The requirement of this circuit design does not mention the gain, thus I fixed both resistor to 10K. After applying the value into the formula, the magnitude of voltage gain of this circuit is 2. On the left diagram is hardware setup for this circuit design. The power supply diagram is in dual supply mode, set as plus 5 volt and negative 5 volt is used for power op amp. The signal generator is used to form the signal input for diagnosing the circuit design whether it meets the requirements. When signal generator set amplitude at 1 Vp peak, which is 0 pi volt V peak in 1 kHz frequency, the wave is captured on oscilloscope. In the diagram, there is two waveform, which is yellow waveform represent channel 1 input voltage, while blue waveform represent channel 2, which is output voltage. As the measured reading shows, Vmax for Vin is 0.52 volt peak, and for Vout is 0.72 V peak. Now let's talk about the frequency response graph. On the left side is simulation result, which using Proteus simulation app form, while on the right side are practical frequency response graph, which are formed by collecting data from practical circuit using oscilloscope probe on V-in and V-out. To form a practical frequency result, from the last slide, the voltage gain in decibel at 100 Hz frequency is almost nearly 6 dB. To get the value of 6, sub in the formula of voltage gain, which is V out over V in, and the formula of voltage gain in decibel is 20 times log V out over V in. In this table, the first highlighted are the amplitude voltage. For my V in is 0.4 V peak and V out is 0.96 V peak. Sub these two values into the voltage gain equation. After calculation, we will get 1.95 in voltage, while voltage gain in decibel is equals to 5.8, which is approximately 6 dB. Thus, the magnitude of the voltage gain against the cutoff frequency is 5.8 dB. Minus 3 dB will get 2.8, which is approximately 3 dB. That's all for this video. Thanks for listening. Like and share if the video is helpful. Bye.